A bicycle pump forces air into the confined space of the tire. As more air is added to the tire, the pressure increases. The tire's volume increases slightly, and the air becomes warmer. These observations are predictable properties of gases, and, as we explore in this chapter, they are described by the gas laws.
This leads us into what's called the ideal gas law. And of all the equations in this chapter, the ideal gas law is the one I use the most. I can actually derive Charles' law and Boyle's law and Avogadro's law from the ideal gas law. So this is a real handy kind of equation for me personally. And if you're going to do something like pump up a bike tire, which I certainly have done before, the pressure is affected, the volume of the gas is affected as you pump more quantity, moles, which are N, into it, and the temperature does change a little bit as well. And all of those things are related by that big R. And this big R is different than the R we saw in organic chemistry, which represented a generic alkyl group. This R is specific to gases. It's called the ideal gas law constant, or the gas law constant, and we'll talk about that here in a little bit. But PV equals nRT, super handy equation for this section. R, again, is called the gas constant, universal gas constant, different things like that. Depending on the kind of units you use, the actual value of R will change as well. In this chapter, we're going to use the top value there of R a lot, 0.082057. I call that the gas R because it's the one you use with gases. And R equals PV over NT. You can see there that volume, liters, pressure, atmospheres on top, moles, and Kelvin temperature on the bottom. So R equals PV over NT. It's a nice way to remember what the ideal gas law equation is if you need it. Now, in later chapters, we're going to use the R that's just underneath it a lot. I'm going to call that the energy R. And 8.3145 joules per mole Kelvin is another version of R we're going to use quite a bit. In this chapter, it's all about 0.082057. But like I said, we're going to be using that 8.3145 number a lot in the future. In physics, you'll talk about a way to turn liters, atmospheres into joules. Liters, atmospheres is actually a type of an energy, joules. And that's not so important for us right now, but in the future, you might see that. Just realize that there's a way to convert liters, atmospheres into joules, turning 0.082057 into 8.3145. I highly recommend you memorize R. In this chapter, you will need 0.082057 a lot, and you don't want to have to keep looking it up or Googling it all the time, all right? And you might get confused and use other versions of R down there. So make sure you know it. If you have room in your brain / calculator, throw in the energy R as well, because in later chapters, that's going to dominate our discussions. This is a kind of problem where ideal gas law can be really useful. Let's say that we wanted to fill a small room with nitrogen gas, all right? And the small room is 960 cubic feet. So that would be feet cubed. Excuse me, but that's a real ugly unit. So I converted it for you there. 960 cubic feet equals 2.70 times 10 to the 4th liters. And we want to fill the room up to a pressure of 745 millimeters of mercury at 25 degrees Celsius. And again, the question is, how much nitrogen do we need? So how much nitrogen means moles, all right? Because moles is a way to do that. We could convert moles into grams, kilograms, stuff like that, but moles is going to be our starting point. We will need the R value, so 0.082057, that's going to come in really handy here. So in a problem like this, what I would do, first get everything into the right kind of units. And if you look back at those values that were up there, the liters value is fine. All right, don't use the cubic feet like ever. Those are horrible units, but in my very biased anti-imperialistic unit perspective. but liters is great. Remember that R is liters atmospheres per mole Kelvin. So liters and liters, no problem. But pressure, we're going to have to convert millimeters of mercury into atmospheres. And again, if you remember from earlier, that's 760 millimeters of mercury per atmosphere. So we'll do that. We're also going to need to convert Celsius into Kelvin, like we talked about earlier. And again, 273.15 added to 25 will give us the right kind of value. In this problem, here are the converted units. Volume again in liters, you don't have to change. You do have to change the temperature to Kelvin. You do have to change the pressure into an atmosphere. And so remembering that the 760 millimeters of mercury per atmosphere is considered an exact conversion, 3 sig figs and 745 millimeters of mercury creates a number that's 3 sig figs, 0.980 or 9.80 times 10 to the minus 1. No problem. Also realize that when you add and subtract, sometimes you end up with more sig figs. When you add and subtract, it's always about the doubtful digit. 25 Celsius stops at the 1 spot, and that means our answer, 298, also has to stop at the 1 spot. But in the process, we went from 2 sig figs to 3 sig figs, and that's very, very normal. You could have also added 273.15, but because the answer stops at the 1 spot, you would cut off the 0.15. 298 Kelvin is the right answer here. So now that you've got everything in the right values and you know R, we can solve for N. N equals PV over RT, and we've got all the right kind of units that we need. So here's the values we calculated earlier. There's also the R value, 0.082057, and the moles comes out to be 1.08 times 10 to the third moles, all right? And if you're curious how that means, you can turn that into kilograms of nitrogen. It's about 30.3 kilograms. And how I got that number, I took the moles, I multiplied by the molar mass of N2, which is about 28 or so grams per mole, and then I converted grams to kilograms by dividing by 1,000. So this is the way to calculate how much N2 you need to fill up that small room. Here's another kind of problem you might see. This one involves stoichiometry. Now, stoichiometry is just a way to convert one kind of unit into the other. And this was something we did in Chem 221. So in this problem, we've got some hydrogen peroxide, H2O2. And hydrogen peroxide is a liquid at room temperature. But in this problem, it's being converted into gaseous water and gaseous oxygen. So what we're going to do here, because we're looking, if you read through it a little bit, we're looking for the pressures of the gases, all right? We're going to have to convert the grams of liquid into moles, use stoichiometry to go moles of the liquid to moles of one of the gases, and then finding the pressure from there, stuff like that. Remember that ideal gas law only works for gases, so we can't use PV equals nRT for H2O2 here because that's a liquid. PV equals nRT only works for gases, so it will work for water and oxygen, but not the hydrogen peroxide. So what we need to do here is turn grams of H2O2 into moles of H2O2. But first, this is actually a practical problem. This bombardier beetle, and I don't know like anything about insects, I'll be honest, but anyway, apparently this beetle uses the decomposition of hydrogen peroxide to spray its enemies, and it sprays out pretty good because all these gases being created just, I'm sure, shoots out like a hydrant. So that's kind of interesting unto itself. Anyway, what we want to do in this problem, we've got to figure out the moles of H2O2 first, then we'll use a 2-to-2 ratio to get to moles of water, or a 2-to-1 ratio to get moles of oxygen. And from there, we can solve for P, pressure, in the ideal gas law. P equals nRT over V. If we use all the right units, we're going to be good to go. We're going to do a lot of 25 degrees Celsius calculations. Room temperature is usually seen or felt to be 25 degrees Celsius, even if it's not quite right. And 25 Celsius is 298 Kelvin. So get ready. You're going to do a lot of 298 Kelvin temperature values if we're starting at 25 degrees Celsius. grams to moles of the liquid, 1.1 gram per mole. H2O2, about 34 grams per mole. That 34 number comes from 2 hydrogens plus 2 oxygens. So on the periodic table, hydrogen is about 1 gram per mole. Oxygen is about 16 grams per mole. So 2 times 1 for hydrogen plus 2 times 16 for oxygen. That's where the 34 number came from. 2 sig figs in 1.1 grams. So 2 sig figs in our moles, 0.032 moles hydrogen peroxide. Now we can convert it into oxygen or water. It doesn't really matter. Let's do oxygen first because I can show off a weird stoichiometry. All right. Stoichiometry is a way to convert, in this case, from reactants to products. The equation at the top there says that 2 moles of H2O2 that decompose will create 1 mole of oxygen. So that's where the 1/2 ratio came from. It's the 2 right here, and there's like an invisible 1 in front of the O2. That's what the 1 part came from. So 0.032 moles H2O2 should create 0.016 moles of oxygen. Finally, pressure of oxygen, like pressure of all gases, equals nRT over V. So we can use the 0.016 number for pressure of oxygen times R times, you guessed it, 298 Kelvin, 25 Celsius in Kelvin is 298, divided by the volume, 2.50 liters. And if you calculate that, 0.16 atmospheres. So the pressure of the oxygen gas in this example from 1.1 grams of H2O2 will come out to be 0.16 atmospheres. We also want to calculate the pressure of the water. And what we could do is we could do the same kind of process we did earlier. We found moles of H2O2. You could convert that into moles of water, and it's 2 to 2 or 1 to 1. And from moles of water, you could plug that into P equals nRT over V to calculate the value. But there is a quicker way here. All right. We saw that by Avogadro's hypothesis that volume and moles are proportional. So as the moles went up, then the volume of the gas went up. So 1 mole had 1 volume, 2 moles would have twice the volume. Well, you can do the same kind of thing for pressure. If the volume is constant, which it is in this problem, as the moles goes up, the pressure goes up. So you can also use Avogadro's hypothesis as a way to think about the pressure and mole changes. And why that's important here is that 1 oxygen is also going to be accompanied by 2 waters. It's a 1 to 2 ratio. So if the pressure of oxygen was given, which we just calculated on the last slide, the pressure of water should be twice as big because the mole ratio is twice as big. The pressure should also be twice as big. So if the pressure of the O2 on the last problem was 0.16 atmospheres, the pressure of water will be twice that number, or 0.32 atmospheres. So you can use stoichiometry sometimes to calculate these pressures. And if you don't believe me, by all means go back and figure out what the pressure of water would be based on the stoichiometry. So go back to the moles of H2O2, which will equal the moles of water. P equals moles of water times RT over V. You should get 0.32. But of course, instead of doing that, using stoichiometry, a lot easier. Also notice that the total pressure of the flask would be 0.32 atmospheres plus 0.16 atmospheres. So you would have 0.48 atmospheres total. And we'll talk about that here in a little bit. Dalton was the one that figured that the sum of the individual gases equals the total pressure in a gas. So if the water gas was 0.32 atmospheres, and that's what we looked at earlier, plus the pressure of the oxygen 0.16 atmospheres, the total pressure of all the gases will just be the sum of the individual ones, 0.48 atmospheres. This is called Dalton's law of partial pressures, and all it means means is that you just add up the individual pressures to get the total pressure. In the lower picture right there, it shows 3 different gases at those 3 different pressures. A kilopascal is another type of pressure that can be measured. But if you mix all 3 of those together, then you'd have a total of 1,350 kilopascals, which is equal to 300 plus 600 plus 450. So Dalton's law of partial pressures just is adding up all the individual pressures to give the total pressure. And sometimes this can be helpful. So if you knew the total pressure was 0.48 atmospheres and you knew you had 0.32 atmospheres of water, then you could find the oxygen by going 0.48 minus 0.32. That can be kind of handy sometimes in chemistry. So here's a question. Diborane reacts with oxygen to give boric oxide, which is B2O3, and water. And notice the stoichiometry there, 3O2, B2O3, 3H2O, etc. So here we're mixing B2H6 and O2 in the correct stoichiometric ratio. What that means is for every mole of B2H6, we have 3 moles of O2, okay? And the total pressure of the reactant mixture is 200 millimeters of mercury. So what that means is that the total pressure of the B2H6 and the 3O2s is 200 millimeters of mercury. Then it says, what's the partial pressures of the reactant gases? Okay, at first this might seem a little bit weird, but remembering that the pressure of B2H6 plus the pressure of O2 equals 200 millimeters of mercury, we can actually figure this out, assuming that they're at that correct stoichiometric ratio. And if you go back to that ratio, it's 1 B2H6 for every 3 moles of oxygen. So if it's 1 to 3, you can think about there as being like 4 equivalents of gases, all right? And of the 4, 1/4 will be B2H6 and 3/4 will be O2. Now, 200 millimeters of mercury divided by 4 is 50 millimeters of mercury. And that literally is the pressure of 1 equivalent of gas. And B2H6 would be 1 equivalent, so that would be 50. 3/4 times 200 would give you the 150. So the answer here is going to be answer D. And again, how we did that is that the total moles on the reactant side essentially is 4, all right? So 200 millimeters of mercury divided by 4 is 50. That's the pressure of the B2H6. And if these are at correct stoichiometric ratios, then 1 B2H6 needs 3 O2s, 50 times 3, 150 millimeters of mercury for the O2. This is kind of an interesting way to approach these kind of problems, but it is kind of useful sometimes when you don't know the total pressure, or you do know the total pressure, but you don't know the individuals. So I added up the total moles on the reactant side. 1 plus 3, 4. 200 divided by 4 gave me like 1 value, and that number times 3 gave the oxygen.